Hey guys, this is Mrs. Rajewski. Today we are going to talk about what it means to be a differentiable function. How do we decide if a function actually can be differentiated at a particular point? So let's go back and remember what it means to be a derivative anyways. So let's look at the limit definition of derivative. We say that a function that if it exists on an open interval around x equals some particular value. Now, this could be any value, of course. We're just going to call it a, some value that x could be. If f is differentiable, our function f is differentiable at x equals this random number that we don't really know, it is differentiable there if the limit as h approaches 0 of f of a plus h minus f of a all divided by h exists. So this was our limit definition of a derivative. And remember, h is just a little tiny bit. So this is like between one point and another point that are so close together as nearly nothing. If this limit exists, we denote it by f prime of a. So that means that f prime of a, or that first derivative of f at that point a, is the derivative of the function f at x is equal to a. If you remember, derivative is just a fancy way of saying like the slope or the rate of change at a particular point. So if f, our function, is differentiable at a for every single a that exists within the domain, then we can say that f is a differentiable function. That is a fancy mathy way of talking about it. But before we begin, let's look at that limit experience that's happening here. So this is actually kind of a fun proof that we can do. In my opinion, of course, we can prove the limit as h approaches 0 of the cosine of h minus 1 all divided by h is equal to 0. Okay, so normally if we're calculating a limit, we would try substitution first, right? But if I substitute in a 0 for h, the cosine of 0 is 1, and then 1 minus 1 is 0. And then if we substitute in a 0 for h here, I get a 0 in the denominator. So this situation is bad news bears. Okay, so far we haven't discussed how we can calculate the limit if we get this type of a form for an answer with substitution. And it's not really factorable, right? Like we might be able to use some trig identities and whatnot, but we're not going to get out of this form. This is actually called indeterminate form. So what do we do if our strategies for calculating limits doesn't really work in this situation? What I'm going to do is I see this numerator, the cosine of h minus 1, and I think, okay, let's see what I can do with that. Let's multiply the top and the bottom by a conjugate. So specifically conjugate is the same ends with the different sign in the middle, right? So let's try multiplying the top and the bottom by the conjugate of the cosine of h minus 1, which would be the cosine of h plus 1. So I've got my original cosine of h minus 1 over h. And let's multiply on the top and the bottom by the cosine of h plus 1. It's not really like I'm changing anything that much, right? Because any number divided by itself is actually 1. So I really haven't changed the value. The next thing that I'm going to do is I'm going to try and distribute. Okay, so I'm going to distribute, and I get the limit as h approaches 0 of, cosine of h times cosine of h is cosine of h squared. Cosine of h times 1 is cosine of h. Negative 1 times the cosine of h is a negative cosine of h. That's nice. These will cancel out and make a 0. And negative 1 times positive 1 is negative 1. And this is all divided by h times the cosine of h plus 1. Okay, so let's see. Like I said, these are going to make zeros. Cosine of h minus cosine of h. And then I happen to see, what's left on top here? Well, the cosine of h minus 1. sorry, the cosine of h squared minus 1. That's important. Now, cosine squared of h minus 1, this looks pretty familiar to me. So what I'm going to do is I'm going to take an aside for logic. Do you guys remember, and I bet you do, the Pythagorean identities? The Pythagorean identity said that the cosine squared of h plus the sine squared of h is equal to 1. But I don't have cosine squared plus sine squared. I've got cosine squared minus 1. So let's move our 1 over to this side and subtract sine squared over to the other side of our equal sign. Our 1's make 0, these sine squareds make 0, and now I have cosine squared of h minus 1 is equal to negative sine squared of h. Okay, so we can see that cosine squared of h minus 1 is actually equal to negative sine squared of h. I'm going to pop that bad boy in here. Here we go. The limit as h approaches 0 of not cosine squared h minus 1, I'm going to say negative sine squared h, all divided by h times the, ooh, I forgot my s, the cosine of h plus 1. Okay, this is getting good, getting good. What I'm going to do here is I'm going to split the square. You might be thinking to yourself, what? Has Mrs. Rajewski lost her mind? I'm not going to answer that. So we're going to split the square. What I mean by that is, let's take something that we know is a square like x squared. Well, that's the same as x times x, right? And if this were a negative x squared, like we have our negative square here, then that negative is either going to go with the front x or the back x. I'll make it the back x. Okay, so that's just splitting the square. I'll put my parentheses around it so we can really see. So I'm going to split this square. I'm actually going to create like two fractions here. So negative sine squared of h is really the sine of h times negative sine of h. And I'm making two fractions, h and cosine of h plus 1 will be the denominators. Now, haven't really changed this up. I've just split these fractions apart a bit. If I multiply them together, you multiply fractions straight across, I still have this exact same result. Sine of h times negative sine of h is negative sine squared of h, and h times the cosine of h plus 1 is h times the cosine of h plus 1. So I haven't went crazy. But look what fanciness I've done. If you recall from the properties of limits, we know that if we're taking the limit of this whole thing as h approaches 0, that's the same as the limit as h approaches 0 of the sine of h divided by h times the limit as h approaches 0 of negative sine h divided by the cosine of h plus 1. And we know this limit. We've been looking at this before. Fancy seeing you here. We know the limit as the sine of h approaches h divided by, we know the limit as h approaches 0, the sine divided by h is actually 1. When your angle and the denominator match, it's 1. So what we really need to find out is what this is. And luckily for us, we're not just having an h in the denominator anymore like we were back up at the beginning. Now we can substitute in that 0. So I'll get the negative sine of 0, if I'm going to take the limit, divided by the cosine of 0 plus 1. Now, negative sine of 0, that is like, I guess we could write negative 0. You know that doesn't mean anything. It's just 0. Cosine of 0 is 1. 1 plus 1 is 2. So I've got 1 times 0 divided by 2. That is 0. And that, oh my goodness, Ryeski, is what we were trying to show. See? And now we're done. Let's move along. Okay, so now we've got this next situation. So let's say if a function is differentiable at x is equal to a, then that means it is also continuous at x is equal to a. So basically, if it's differentiable, it tells you that it's continuous. The reverse is not true. Just because a function is continuous doesn't mean that it's differentiable. But if we do see that a function is differentiable at a particular point, then we know, very, very much know, that it is also continuous. So let's take this continuous function. This is y is equal to x to the 1/3 power. This is a continuous function. I can graph it without picking up my pencil. I can take the limit as x approaches 0, and in both directions, they're both going to go to 0. This is a continuous function. If we substitute in 0, we get the same result out as the limits. So we are definitely continuous. However, this function is not differentiable. This derivative, the slope here, is undefined, so it's not differentiable. At the point where x is equal to 0, we have a vertical line slope. Okay, so functions are undefined in at least 3 situations. Vertical lines, such as this situation, okay, and corners and cusps. Cusps are the little, the point at the heart here where you've got 2 curved lines reaching up, okay? So with corners and cusps, the reason that the function cannot be differentiable there is because at those 2, the slope changes its sign too quickly. We're negative, negative, negative slope, and then suddenly we're positive, positive, positive slope. So in fact, right there at that, I don't know if it's called a vertex, but right there, where that point is, the slope is negative approaching that value, and it is positive approaching it from the other direction. So it's just too much of an instantaneous change in sign. So how can we test for differentiability? It's actually pretty easy. We're going to make sure, first of all, that the function is continuous, where x is equal to whatever value we're checking the differentiability at. Then we're going to check the left-hand derivative and the right-hand derivative. So this sign right here, the little negative sign there, this represents the left-hand derivative. I'll call it the LHD. And with the little positive sign underneath, that is the right-hand derivative. So I'll call that the RHD. So both of these derivatives have to exist, and they have to be equal. So not only do they have to exist, they have to be equal. With that x to the 1/3 problem on the last page, the derivative didn't exist at x was equal to 0 because it was a vertical line, and a vertical line has a slope that does not exist. Okay, so I'm basically going to write this down as a 4-step plan. I know you're thinking, 4 steps. This is terrible, Ryeski. I know I didn't make it up, but I'm going to try and make it easy for you to follow. So number 1, you need to show that it's continuous. Number 2, you're going to find the left-hand derivative. Number 3, you're going to find the right-hand derivative. And last step, we're going to show that the left and the right-hand limits exist and are equal. Okay, so step number 1, we're going to show it's continuous. So first of all, we're looking at the function f of x is equal to x minus 1 raised to the 1/3 power. We want to show that it's not differentiable at x is equal to 1. Okay, so let's calculate f of 1 first of all. We have to show that this exists. If it doesn't exist, it's not even continuous. And if it's not continuous, it's not differentiable. So let's see, f of 1 is equal to 1 minus 1 to the 1/3 power. Well, 1 minus 1 is 0, and 0 to the 1/3 power is 0. Now let's see, the limit as x approaches 1 from the positive direction of this function. Well, as x approaches 1 from the positive direction, we are going to get 0. And the limit as x approaches 1 from the negative direction is also 0. And since 0 equals 0 equals 0, these all are the same, f of x is continuous. At x is equal to 1. All right, so now let's find step number 2. Let's find the left-hand derivative. Okay, the left-hand derivative, well, we already know. Like if we graph this thing, let's go ahead and show it. Oh, come on, my calculator. Oh, there we are. Matrices. So if we're going to graph this, y equals, clear. Okay, so as x is getting closer and closer and closer to 1, look what's happening to my slope. Okay, it's getting closer and closer to this vertical line. In fact, right there at 1, I do have a vertical line. So the left-hand derivative, as I come up at it from the left, my left-hand derivative is undefined. And honestly, I could stop right here because in order for this to be a differentiable function, it has to exist. Both of them, the left and the right-hand limits have to exist. And we can see it fails right now because it doesn't exist. But I'll just continue going. I'm now going to find the right-hand derivative. And similarly, if I come at this graph from the right-hand side now, I see that as I approach 1, I also have that vertical line. And I can zoom box this thing. Zoom box is my favorite way to zoom in. I'm going to get a little closer and see what's really going on here. Yep, you can kind of see that vertical line. Maybe zoom box it again. You can really see that vertical line now. So this is also undefined. And then we can continue on to step 4. We're going to show that step 2 and step 3, the left-hand derivative and the right-hand derivative exist and are equal. Well, I mean, they do both not exist, so that I guess is equal, but they don't exist. So not differentiable. Easy peasy. Let's continue. So now we have to prove that the function, the piecewise function that we're given here, is continuous but not differentiable. Well, we're going to follow that same 4-step plan that we did on that last problem. Okay, so that's kind of the nice thing about having a plan. We can use it over and over again. So let's start by proving that it's continuous. And if it's not continuous, we can stop there because it has to be continuous. I mean, it definitely tells us in the problem anyways how it's set up that it's going to be continuous and then not differentiable. So I'm assuming that either my left and my right-hand derivatives are not going to match, or maybe they're not going to exist, or maybe one will exist and the other doesn't. Something's going to have to give. So looks like we're focusing on what's happening where x is equal to 0. So I'm going to find f of 0. Now, this is interesting with the piecewise function. We're going to use the top function for all x values that are greater than or equal to 0, and we'll use the bottom function if any x value is less than 0. Since this x value actually equals 0, I'm going to have to use this top equation because that's the one it tells us to use when x equals 0. So f of 0 is equal to 0. Just plugging in a 0 right here. Okay, now let's calculate the limit. The limit as x approaches 0 from the left, well, if we're coming at 0 from the left-hand side, those are numbers that are smaller than 0 all the way until we get to 0. So that's the bottom equation. So that means f of x is equal to negative x, right? Because we're using the bottom one. And I'm just going to substitute in a 0. That would give me negative 0 or just 0. So that's my left-hand limit. Let's find the right-hand limit. Now, as we approach 0 from the right, we're coming at it from numbers that are larger than 0. So that's this side, this top equation. So that's the equation we're going to use, f of x is equal to x. Well, I don't want to know about x, I want to know about 0. So find out what's happening. And we just substitute in a 0 for the x. And we get 0 again. So 0, because f of 0 is 0, the left-hand limit is 0, and the right-hand limit is 0. These all match. This is true. So f of x is continuous at x is equal to 0. All right, now let's find the left and the right-hand derivative. So I'll find the left-hand derivative first. Okay, so on the left, to the left of 0, I'm going to use this bottom equation. So this is the one, f of x is equal to negative x. And if I'm finding the left-hand derivative, I'm just going to take the derivative of this. So I'll get f prime of x, and I'm going to put the little negative sign underneath. So this is like telling me this is the derivative as we're coming at it from the left. Okay, and the derivative of negative x is negative 1. Now, I'm not really that interested in just any derivative on this whole function. I'm looking specifically for the derivative where x is equal to 0. So let's substitute 0 in. Of course, since there's no x value here, the substituting in of 0 doesn't really matter. The slope is going to be negative 1 there. Okay. So now let's check out the right-hand derivative. So I've got f of x on the right-hand side, this is just going to be x. The reason why is because on the right-hand side of 0 are the numbers that are 0 and above. And this is telling you when you've got numbers that are 0 and above, you're going to use the top equation. So we take the derivative. This is now going to be the right-hand derivative, so I'll put the little plus sign there. And the derivative of x is 1. Of course, we are trying to find the derivative where x is 0, so let's substitute in a 0 for our x. And it has no effect whatsoever because there's no x value there to sub in 0 to, and we get 1. Now for our final step, we need to show that the left-hand derivative and the right-hand derivative exist and are also the same. So our left-hand derivative was -1, our right-hand derivative was +1. They do both exist, however, they are not the same. My left-hand derivative was -1 and my right-hand derivative was +1. So even though f of x is continuous at x is equal to 0, the function is not differentiable at x equals 0. Alrighty, and this will be our last one. This is actually the last one in our whole unit. So we are going to prove that f of x is equal to the sine of x as long as x is greater than or equal to 0, and it's equal to x squared plus 5x as long as x is less than 0. Okay, so let's check this out. You've got on Desmos now let's see if we can pull it up here, a graph that looks like this. We've got the sine of x everywhere that x is greater than or equal to 0, and we've got x squared plus 5x everywhere that x is less than 0. So I'm going to go ahead and take a snapshot of this and include that in our conversation. Kind of cool, huh? Love Desmos. So here we have our function. Okay. So everything looks continuous, right? I mean, we're coming along here. Everything's beautiful. Everything is beautiful. The only part that we're maybe worried about is where these two graphs connect, right? So we want to see what's happening right here. So let's check it out. So first things first, just like we did on the last one, we want to find and see if it's continuous at 0. So I've got f of 0, right? When x is actually equal to 0, we're going to use this top equation. We know that because the equals part is there. So I've got the sine of 0. Well, sine of 0 is 0. Fantastic. Now, let's calculate the limits. The limit as x approaches 0 from the left-hand side, that's asking you about, well, here, let's put it like this. That's asking you about the left-hand side, x squared plus 5x. We can substitute 0 in here. We get 0 squared plus 5 times 0, and all that is equal to 0. Now let's look at the right-hand limit. This is going to use the sine of x because that's where all your values to the right of 0 are. So that'll be like the sine of x. So that's going to give me the sine of 0, which again we know is 0. So we see that 0 is equal to 0 is equal to 0. This is a continuous function at x is equal to 0. So now let's check out those derivatives. Okay, we'll go with the left-hand derivative first. The left-hand derivative is going to use that bottom function because that's where the x values to the left of 0 are. So if I want to find that left-hand derivative, I'm going to take the derivative of that left-hand side. That's going to give me 2x plus 5. Okay. And of course, we're not interested in the derivative of x. We're looking at the derivative at 0. So let's substitute 0 in there for our x. And that's going to give me 5. So my left-hand derivative is 5. So to the left of 0, as we're approaching 0, the slope of this function is about 5. Now let's check it out from the right. So on the right, that's where x values are greater than or equal to 0. So we're going to use f of x is equal to the sine of x for the right-hand derivative. And I'm just going to calculate that derivative. I'll put a little plus sign underneath so we know that we're talking about the right-hand derivative here. And the derivative of sine is cosine. Oh, I don't know why my pen made that mark there, probably because I wrote it. And of course, we're not interested in x, we're interested in 0. So let's substitute 0 in for the x and see what we get. I get the cosine of 0. Ooh, that's 1. What that means is, as we're approaching 0 from the right-hand side, the slope of this function is about 1. And you can almost see it here, right? It kind of looks like it's a 1 there, this positive 1-to-1 slope there. I like it. What I don't like is the fact that for step number 4, I have to show that these are the same, and they're not. 5 does not equal 1. The left-hand derivative does not equal the right-hand derivative. Therefore, f of x is continuous, but not differentiable at x is equal to 0. And that, my dears, is all I have for you. Hopefully it makes a little bit more sense now, and seeing that 4-step strategy in action clarified some things for you. Tonight, I'd like you to please do your day 10 homework. This is on differentiability. It's on my lab in mastering. And good luck with your study guides. I know you're going to do great. Have a phenomenal day.